Hi everybody. So I just wanted to talk a little bit about section 11.4. This video is on inference about two population standard deviations. So we looked at the inference about two population means in the last two sections. So these will be our objectives: to find the critical values of what's known as the F distribution, to test hypotheses regarding two population standard deviations. So let's take a look at the first objective here. So we're going to deal with something called the F distribution here, and there are a couple of requirements for testing claims regarding two standard deviations. So the samples have to be independent, simple random samples, and the populations from which the samples are drawn are normally distributed. The population from which the samples are drawn is not normal. Do not use inferential procedures discussed in this section. Again, we'll have to use non-parametric tests as mentioned earlier, which are in chapter 15. So let's look at some notation here used when comparing two population standard deviations. So sigma 1 squared is, remember, that's sigma is the standard deviation, so sigma squared would be the variance. That's the variance for population 1. This is the variance for population 2. This stands for the sample variance for population 1, and this stands for the sample variance for the population 2. And then n and 1 and n2 are the sample size for populations 1 and 2 respectively. So if sigma 1 squared equals sigma 2 squared, and S1, the sample standard deviation for sample 1 and the sample standard deviation for sample 2 are sample variances from independent random samples of size n1 and n2 respectively, drawn from the normal population, then this statistic, which we'll denote by F, which equals the two sample variances divided by one another, follows what's known as the F distribution, with n minus 1 degrees of freedom in the numerator and n sub 2 minus 1 degrees of freedom in the denominator. A couple things about the F distribution is that it's not symmetric, and the F distribution is skewed right. If you look on the upper left-hand corner of page 568, there should be a graph that describes what the F distribution looks at for various degrees of freedom. We'll look at that here in just a minute. And also all these characteristics are stated in a purple box on that page as well. The shape of the S distribution depends on the degrees of freedom in the numerator and denominator. This is sort of similar to the chi-squared distribution and students' T distribution, whose shape depends on their degrees of freedom, but again, in this case, it will depend on both the numerator and the denominator. And the total area under the curve is 1, so it is a probability distribution just like other distributions. And the values of F are always greater than or equal to 0, similar to the chi-squared distribution. So here's what the F distribution will look for various degrees of freedom in the numerator and denominator. So the N here stands for degrees of freedom for the numerator. DFD stands for the degrees of freedom in the denominator. When you're looking up the F value, it will depend on a couple things. It will depend on the alpha value, and then it will also depend on n sub 1 minus 1 and n sub 2 minus 1. And then again, this will be an area, you'll have an area of alpha to the right of the critical F value. To find the critical F value with an area to the left, you'll basically need to use this formula. So essentially, if this is like 5%, then alpha would be 95, and then what you do is you switch the 2 degrees of freedom of the numerator and denominator and divide by 1. We'll hopefully look at an example of that. So let's look at an example here. So let's say for a right-tailed test with alpha equals 0.1, and the degrees of freedom in the numerator are 8, and the degrees of freedom in the denominator are 4. And then let's say we want to do two-tailed tests. So let's look at this right-tailed test first. So in this example, the alpha is 0.05, the degrees of DFN is 8, and DFND is 4. So that would be 0.184. So again, you just look that up in the table. There's an example of that on page 569 in your book. and that would correspond to an F value of about 3.95. Now for the second one, if you look at this, there is no corresponding alpha value for that in the table, right? So the alpha values are broken down into like 0.1 and 0.05, 0.025, 0.01, and 0.001. There's nothing for 0.025, so what you'd want to do is compute 1 over that number, which again would correspond to this being 0.95 and this being sorry, there's nothing for 0.975 in the table, so you would compute this, switch the degrees of freedom around. Now this number you can look up in the table, that will give you 2.57, and then it's just 1 over that number. One thing to note here is that the degrees of freedom is not found in the table. We follow the practice of choosing the degrees of freedom closest to that which is desired. If the degrees of freedom is exactly between two values, just find the average of the two values. So that brings us to our second objective, which is the test regarding two population standard deviations. So to test hypotheses regarding two population standard deviations, again, there are certain conditions that have to be met, and again, this procedure is outlined in the purple box on page 570. So again, in most cases, I think you can assume that these conditions hold, but again, something you should really verify when doing this in reality. So the samples, again, are obtained using simple random sampling. The sample data are independent, and the populations from which the samples are drawn are normally distributed. So again, we can have three kinds of tests: two-tailed, left-tailed, or right-tailed, just as before. And then to select a level of significance alpha based on the seriousness of making type 1 error, again, alpha will be given to you typically. Compute the test statistic, and then use table 8 to determine the critical values, again, with the appropriate degrees of freedom. And remember, one degree of freedom should be along the top. That should be the numerator, and then degrees of freedom of the denominator will be along the side. For the two-tailed test, again, remember this isn't symmetric, so you can't just double the areas here if it's a two-tailed test. For the left-tailed test, again, you may have to use the formula that we talked about earlier. For right-tailed test, again, you should be able to just look that value up in the table. And then again, you can either use the classical approach or the p-value approach, but in this case, and from now on, typically we'll have a high reliance on technology because the p-values will be harder to compute. But if the p-value is less than the alpha value, we'll reject the null hypothesis. So very similar to other tests. Again, the only main difference is the test statistic is the variance, the sample variances divided by one another squared. And then don't forget to state the conclusion. Couple words of caution here is the procedures we just talked about are not robust, so if the data isn't normal, that might adversely affect the test results. And so you really should verify that normality is satisfied before conducting the test. So let's look at an example. So we'll go back to that example of the state quarters, and let's say that a researcher wants to know whether state quarters had a standard deviation weight that is less than the traditional quarters. So he randomly selects 18 state quarters and 16 traditional quarters, and we'll take a look at the data obtained on the next slide. But a normal probability plot indicates that the sample data could come from a normal population that's normal. So again, typically you won't have to verify those conditions. And then keep in mind in this case alpha is 0.05. So again, here's the data table for the 18 state quarters and the 16 traditional quarters. So the researcher wants to know if the state quarters have a standard deviation weight that is less than the traditional quarters. So this would be our hypothesis. So this would be a left-tailed test. Again, remember the level of significance is 0.05. Compute the test statistic, and this is what we get. And then if you're using the classical approach, you'd want to compare this test statistic to the value that we would look up in the table. So in this case, alpha is 0.05, so that means we want to find f of 0.95. Remember the number of traditional quarters was 18, so that would give you n minus 1 degrees of freedom there, and then the number of state quarters of 16, so that will give you 15. Now again, if you look up this value in the table, you won't be able to find it in that table 8. So what we will do is use the formula 1 over 100% minus this, which will give you 5%, and then switch the degrees of freedom around, will give you 1 over 240, which gives you 0.42. And then again, compare that to the calculated value we got there. And in this case, since the test statistic is greater than the critical value, we do not reject the null hypothesis. Again, if you're going to use the p-value approach, again, I guess you could try to use tables to calculate the p-value, but using technology will typically be more accurate. And so again, the solution should be the same whether you're using the classical or the p-value approach, right? You would reject the null hypothesis. So again, and then again, don't forget to state the conclusion in words. So there's not enough evidence to conclude that the standard deviation of weight is less for the state quarters than it is for traditional quarters. All right, well that wraps up section 11.4. So the next section we'll look at is section 11.5, which basically kind of puts all the previous sections together. And so the main thing you'll have to do here is determine which is the appropriate method to use. So again, remember that you have several various test statistics. This slide should hopefully summarize what you want to do, right? So if you're looking for proportion, if you have dependent or independent samples, you use the appropriate statistic. Sigma, so the standard deviation or the variance, you would use this test statistic as we just saw. And the mean, again, you'll have independent and dependent cases. So, all right, well, I hope that makes sense. If you guys have questions or anything, let me know.